Okay, thank you for coming back. So if you have any questions about what I presented yesterday, it's a good point to ask them, maybe. Otherwise, I will continue where I stopped here yesterday. So I stopped after lexicographic preference trees, which was it is a nice model, fairly intuitive, simple, with nice computational properties and quite easy to learn. With the only drawback that it is maybe, well, expressivity comes at a high cost with this model, because you must allow for nodes with maybe large number of variables, which then makes it more difficult to learn and to reason with. But anyway, it is so I think I covered all that. Yes. Did I do that or not? I can't remember. Did I present us learning of LP trees? Yes, huh? I did. And learning from pairwise comparisons too, or not? I'm not sure about this one. I presented. Yes. Okay. Good. Yeah. Okay. Okay. So I start here. So at last, one slide with a nice picture. So this is I'm going to introduce a language which is a bit more difficult to work with, which has a semantics which is both easy and not easy. Well, it is difficult to compute and not so easy to understand at first. I'll show some things, a few things on an example. So this example is about planning a short holiday, and it's for somebody who has two options for the departure date, say, which can be at the weekend or on a Monday. Don't ask me why. Who can take a car or a train, and who has three possible destinations. So they are all around Toulouse. They can all be reached by train from Toulouse, Figeac, Le-Luron, and Albi. And this is a picture of the train station at Le-Luron, which is in the mountain north of Toulouse. Okay. So see, the language, it is a bit of it's a kind of logical language where you express your preferences with formulas like this one. So you have three parts in the formula. Essentially, here you are going to say that you prefer some values to other values. So you have some values for, let's say, one variable W, and here you have another value. And this statement says that you prefer this to that, but in some context. And the two other parts here enable one to put some context on the preference. So this is a condition. So this will be a formula which involves the other variables. And when some condition alpha is met, then this is going to hold. And this is another kind of, this is more a relaxation somehow of the general setting. I will talk more about that later. But essentially, it says that if I have to compare two alternatives that satisfy the condition alpha, whatever the values these two alternatives have for the variables in V, I prefer W to W prime. So let me give some example. So here, this formula says that at the weekend, I prefer to go by car than by train. That's an easy one to understand. This one says that just says that I prefer the combination. I prefer to go by train to Le Lioran rather than going by car to Figeac. And for instance, this one gives the preference that at the weekend, so I can complete these two sides, but I must complete them with the same thing. Weekend, for instance, but I would also have the preference on Monday. If I put Monday here and Monday here, the preference still holds. So it is called what ceteris paribus preference statements, which means for all other things being equal. So here for the date being equal on both sides, I prefer to go by train to Le Lioran than rather than drive to Figeac. I'll come back to the semantics a bit more detail. There is a slide with something a bit more detailed than that. And finally, the last one, which says that on Mondays, I prefer to travel by train rather than by car. And this means whatever the destination. Wherever I go, I prefer to go by train rather than by car. So this is the intended meaning of these formulas. A bit of syntax. Well, it's not. So this is a condition. So alpha is called the condition, and we assume that we have a set U, which is the support of the condition, which is the set of variables that appear in it. We have something that I call free attributes. There is no real set name for that. And then we have the swapped attributes, because these are the attributes that are going to change when I do the comparison. And of course, these three sets must be disjoint. Okay. So now I come to the semantics. So the semantics is here, but I've got something which I think is nicer. So, well, just one thing about the semantics. The semantics says, if I have a formula like that, I will compare all pair of alternatives, such that the one on the left has W, the one on the right has W prime. They must both satisfy the condition alpha. This is a logical entailment. So essentially, it means that the values that these two alternatives have for the variables in U must be a partial model of alpha. And then they can be different on the attributes that are in none of the three sets here. Sorry, they must be equal on the other attributes. So it's not that easy. So this is for one statement, and then the global semantic. If you have a set of statements, you're going to take the transitive closure of that, the reflexive and transitive closure of that, so that you have an ordering. So here, no, am I going back? Yeah. So with this this in mind, so if I ask to compare these two alternatives, so Monday car Figeac and Monday train Albi, this one is fairly simple because I can use this statement that says that on Mondays I prefer to go by train rather than by car. So on Monday I prefer to go by train rather than by car, and whatever the destination here, A and F can change, doesn't matter. So this one is correct. Something a little bit more difficult. So this was just application of one statement. Here there is we will have to use the transitivity of the relation. So this statement says that W. Well, the question is which one of the two is preferred to the other one. It's not that easy to see, I think. If you have a W, so at the weekend, suppose you have the statement, you have the alternative weekend car Le Lioran. It is better than, what can I change? What can I swap if I start from this one? What can I swap to get something which is worse. Weekend, car, well, nothing actually. Yes, I can change here because it is the weekend, so I can change car to train. So this one is better. Weekend car Le Luron is better than weekend train Le Luron. When I am at weekend train Le Luron, what can I do? This is going to be better than weekend car Figeac because I have this statement here that allows me to do that. When I am at weekend car Figeac, what can I do? Weekend car Figeac, I can change this one, weekend train Figeac. So I have this chain. And the weekend train, where am I? Weekend train Figeac, I think that's it. Yeah. Well, anyway, there is the solution here. So weekend, Monday. So I can't remember exactly where. So well, anyway, this is the graph. The idea is that if you take all the statements, each statement enables some comparisons, a few of them. Here we have only 3 statements, but we have all these comparisons that are enabled by these statements. And so we have this graph and we have the transitive closure of the graph. So WCL, where is it? Can't remember. WCL here. So you have WCL, WTL. Yeah, there is a mistake here. WTL, WCF, WTF. So it's not exactly this one. Anyway.
Remember what? Can you have cycles?
In this graph?
Yeah.
It can happen, yes. Yeah. Yeah.
And then with the transitive closure, all these things are.
Not all. You will have some, how do you call that? These strongly connected components that are going to be at the same level. So that's why in the semantics, I usually, here I put a strictly superior, strictly greater than, but because actually the other way around is not true, but in some cases you could have some things that are the same preference, that are.
The question was WCL with respect to WTL.
Yeah, I'm not sure about
so you have
WCL. Oh yeah, there is directly the answer. Yeah. So it must be, yeah, there's something which is funny in the example. Okay. So this transitive closure is it means that of course with the statements you can express a lot of comparison. You have transitivity, but it also means that these things are not easy to reason with, because as you can see, if you want to prove that something is better than something else, is preferred to something else, then you will have to find a path in a graph which has an exponential size, which is not something nice. So in general, there are a lot of many things are hard with many reasoning tasks are very hard with this kind of statements. And there is one thing that make all these things easier. Which is if there is somehow some kind of acyclicity constraint on what is called the dependency graph. So here, if I take these 2 statements, it's a very simple set of statements. You have to the dependency here is that the preference on the variable b depends on the value of a. Okay, so we have an arrow here from a to b. Every time you have a preference statement like that, you will add. Yeah, so you have your graph. The nodes are the variables, and you put an edge, an arc every time you have a dependency. Every time a variable appears in the condition, and the other variable appears in the attributes that are swapped. So here we've got a cycle. These two variables depend. Well, the preferences over these 2 variables each depend on the other one. So now, a usual restriction, if we want to reason with this type of formulas, somehow, and well, we can, if we want to make it practical, we have to have formulas such that the graph has no cycle. So this one is not a nice one because it has a cycle, this one. And so we must restrict to formulas that do not have any cycle, which is not, well, this is easy to check, actually. You can draw the graph in polynomial time and check if it has a cycle. That's not a difficult task. But if it has a cycle, then there are many things that are difficult. So something else about CP statements. There has been a lot of work on that since in the last 20 years, right? And most work on the sublanguage, where the cardinality of the tuple of a swapped variable must be 1. So these have one variable which is swapped. Here it is B, here it is A. I think all the statements that I've put. Now on the example, there was one which is this one is not is not in the class that have is not in this class here because for this statement we had W, the cardinality of W, which was 2. And also we have a conjunctive condition, but this may not be so important. But here the condition is just, well, there is a very simple condition that the value of A must be A. So it is obviously conjunctive. We could imagine something more expressive than just that. But most works consider that there is a conjunctive connection. And the most work use actually what is an even more restricted sublanguage. I'll come back to that later. So as for expressiveness, it is very expressive because, for instance, if I compare to additive utilities, with additive utilities, you can compare everything because you associate a number with everything, so you can compare everything. Here, we have seen the graph clearly shows that there was on the example shows that you have only a partial ordering. Not everything is comparable. So you have, in fact, a lot of incomparabilities in general. And so for the not so nice part of the model, so comparing two alternatives is p-space complete. That was proved 15 years ago. And so that's a basic reasoning task that you can do with this without restriction. You cannot do this with this model. But if we put enough restrictions on the type of formulas that we allow, then it can become easier. Ordering a set of alternatives. So you have a set, for example, in information retrieval, you have your set of documents that have been retrieved, and you want to rank them to present them in the right order to a user. The complexity is unknown in general. So it is, I cannot say if it is hard in general, but because we are going to be restricted to acyclic formulas anyway, if your formula, if the dependency graph is acyclic, then you have it can be done in polynomial time, because there is one query which is easy, and this query it's not comparing two alternatives, but it's a query which is easier, which says, can I say that one is not preferred to the other? So if I come back to the example, for instance, my ordering query would be, if I take these two, is there one which is not better than the other? So here it's obvious. This one is not better than this one. Okay, if I take these two here, is there one which is not better than the other one? Obviously, I can take any of the two. This one is not better than this one. Okay, so this query is not about is there an arrow or is there a path in my graph, but is it true that there is one path is missing in some sense? And actually, and for acyclic graph, it is easy to answer this query. So that's a nice property of the model, because so you can order a set of objects with that query. And finally, still, when you have some acyclicity constraints, then finding the optimal alternative is easy. Why is that? We can see that maybe, or I'll come back to that. No, here I don't have the dependency graph. So I'll do that with, there is another example later with a dependency graph. Okay. Okay. So that's about the language. So now what can you do? It turns out that, so this language is very general, and there has not been a lot of work on learning this very general language. But still, I present it here because I think it deserves maybe some more attention from the people who try to learn preferences because of its generality. The only work that I know on learning this thing, it's not even it's not really machine learning algorithm in the usual sense. So it's kind of lazy learning, for instance, like with what is nearest neighbor, where you don't actually learn anything, you just compare distances, and then you have your output. You don't learn a model. Also, the model exists, but you don't actually explicit it. So here you've got, so suppose you have some kind of, you've got your total pre-order somewhere. And then you've got a set of preference statements. So this work here is restricted to this kind of statement I just mentioned, with one variable swapped and a conjunctive condition. And the question is, just seeing these statements, can I answer if this preference holds? Okay. So, of course, these statements do not represent everything that is here. Okay, it's not just an inference task, because these statements give me some information about that, but they probably do not give me all information about that. So I want to do some generalization. And so a way to do that is to consider an upper approximation of this model. So I define the sort of induced model. In my induced model, which I will not compute, but which is going to give me the answer to that query. An alternative O is better than O prime if for every lexicographic preference tree that is consistent with my statements, the preference holds. So it's quite, it is very strong. It means essentially the idea is that probably this relation here obeys some lexicographic ordering. I don't know it. I have some statements here which do not make it clear that it is a lexicographic preference, but I assume that there is one, and so I will have a very I will consider that this holds as soon as this holds in every LP tree. So this is if I consider one relation here, this is a big relation. Okay, if I have one LP tree, it is a total ordering. So what I'm saying here is that I take this, in fact, this relation here is the intersection of all these relations here that complete, that correspond to LP trees, and that complete this here. And the nice thing is that, so this can be answered fairly easily in polynomial time. I will not, of course, complete all the I will not, of course, compute all the LP trees. There is a polynomial way to do that, just by considering a very there is an algorithmic way of doing the things so that I will check that it holds. Actually, I will check that there is no statement that somehow contradicts my statement here. So this is the only work that I know where one tries to learn something from a set of CP statements. So it's not even learning a CP statement. Okay. So now there is something which is much nicer to work with, which is CPNet. So in CPNet, so this is actually the first model based on these CP statements that I know of, quite early. It has been invented quite 20 years ago around. So in a CPNet, the thing is that I have to give a graph, which is a graph that represents the dependencies that the decision maker has about the preferences over the various variables. So here I give this graph. So I say that my preferences over B depend on C, and they also depend on A. And so this means that the preferences over the two possible values for B, I must give them for every possible combination of A and C, because in the graph, I say that B depends on both on A and C. So my CPNet, if I have this graph, I must give a table that gives all the possible combinations for A and C, and for each of these combinations, say which of B and B bar is going to be preferred. C is independent. There is the preference on C does not depend on anything according to the graph. So I just have to give one statement, which one is better. And for A, of course, I have to give the two statements that are according to that. The two, I have to give the preference for the two possible values for C. Okay. So we still have the same components. We have the statements here. We have the graph. But the big difference is that here, when you define a CPNet, the graph is given at the start. You do not compute the graph from the statements. You give the graph at the start, and then you must have all the tables, all the local preferences that must be given to complete the graph. So because of this completeness, in fact, there are two things that are important here. The first thing is that we are going to restrict to acyclic graphs. Otherwise, there's nothing its queries are hard to answer. And the other thing is that we want something which is very, it is very constrained. You have to express all these preferences. But if you have an additive, a generalized additive utility, you are also supposed to give all the utilities. So it's a bit like that. So now what happens when I want to learn a CPNet from examples of pairwise comparisons, say? So I have my set of comparisons that come, my data. And this is something which is not easy still. I can reason, but learning is not easy. I must learn the dependency graph. So it is something which is very common with all these graphical models. When you want to learn these things, you have to learn the structure, learn how the variables depend on one another, and you have to learn the local preferences. Maybe some of you know about Bayesian networks, for instance. Learning the local probability tables is something very easy. There is just a computation of frequencies, and you've got it. But learning the optimal structure that best fits to the probability that you want to represent is hard. And for CPNets, we can expect that there is this. We can try to learn the structure the dependency graph and learn the local preferences and expect that at least if we've got the structure, then the local preferences are going to be easy. And it turns out that it is not the case. So there have been a lot of work, but not many of them have been successful. So for instance, in this work, which was in 2009, these Greek people, they tried to do that. But they only succeeded in a very restricted setting because it turns out that even if you got the structure, with CPNet, it's still hard to learn the local preferences. So it makes that a difficult object to learn. Actually, the things that work better is to work with to elicitate, to learning by queries. Why is that? Because if you learn by queries, actually you can ask queries that exactly ask what are the local preferences. Okay, if I come back to this one here, so I've got this graph. Suppose I don't know the table here. I've got this graph. Well, I can ask. Suppose I already know the structure. If I try to elicitate the tables, well, I can just ask what is the preference between C and C bar. Okay, that's a simple query. I can well, simple. It's I'm not saying that it is very convenient for a user if you ask that, but I think it is. Well, this one is easy. And well, of course, the number of queries that you are going to ask, there may be a high number of queries, depends on the in degree of the nodes. But here's the same. For B, I know that this is a structure, so I can ask a decision maker what are the preferences in all the possible combinations. And the same for A. So that explains why learning by queries is somehow more successful with that. Well, still you have to learn the structure, but even with queries, you can learn the structure. So why can you do that? I come back to this. Suppose I don't know the graph for a moment. So I can ask queries what is preferred for A, and then I have to ask some queries. I can still ask different queries where I will ask the user to compare two items, which have, for instance, the same value for C, and then another pair of items. And I'm going to try to elicitate if actually A depends on C. So I can do that for a lot of pair of variables to see which one depends on which other. So I can I will see if for A, for instance, the local preference on A depends or not on C. So learning by queries is possible with CPNet. So there have been quite two works, one in 2009-10 and a more recent one where they try to learn by queries. For one thing which is possible, I'll show you why, is to learn a separable CPNet. Separable CPNet is just that the dependency graph is empty. So if the dependency graph is empty, things are a lot easier. You just have to learn the local preferences for each of the variables. So it's not well, it can still be NP complete, but at least it's we've got an idea how to do that, a practical way of doing that. Okay. Oops. So I say that what is more successful is when you learn with queries. And in fact, I said it is easy because you are going to learn what is in the table. You are going to learn. So what you are going to learn with, so I put it here, is in which condition is it that C is better than C bar? So I am going to learn the swap, actually, exactly how one variable changes when some conditions are met. So for learning by queries, so recall this is with CPNet, you have only one variable which is swapped at in every statement. There is only one. So all the examples that are going to be used are swaps where you have only one variable which is different in O, which has different values in O and O prime. And so you can do that. And even though if you want to have a nice complexity, you also have to restrict the structure. And for instance, if the graph is a tree, then we can learn the model. But if it is not, if we don't constrain the structure, we can still learn, but the complexity is going to be higher. So CPNets, it's difficult to learn. I think it is more difficult to learn than the other models that I've presented so far. Okay, so I don't know what time is it. Okay, so now what I'm going to do, I've presented. So for CPNets, I don't present the exact algorithms because I say that I'm not going to talk about learning by queries, and there is not much working algorithm with learning from in passive learning. But what I want to talk about now is about the complexity for these models. So some of them I gave some algorithms, fairly well, somewhere quite simple algorithm for learning LP trees. It's easy. For learning general additive utilities, you have your set of inequalities, and you try to solve and to optimize an objective. What I want to finish with that is how many samples, what must be the size of the data in order to get something which is good enough. Okay, so I am going to present the pack learning settings because I guess not everybody knows about it here. And then I'll give a couple of results that hold for preference learning in that setting that are a bit different. So it's a bit different from learning a classifier, but the setting at the start is exactly the same. So I'm going to present the pack learning setting for binary classification. And then I'll give a few results about what we can do for predicting the number of examples that you need to precisely learn a model, a preference model. So here, so what we want a guarantee somehow that the model that we learn is probably approximately correct. And this formula, this is written here. So this is my target here with this small symbol above it. And this is the model that I learned with some algorithm. I got an algorithm, it outputs this model here. And I can measure, well, I cannot measure it actually, but the loss, the error, the distance between these two models is well defined, even if I cannot measure it. I cannot measure it because I don't know this one. So I cannot measure the distance between the two models. But at least I've got a definition of this distance. In binary classification, it's just a number of alternatives of objects where they are different. If you take two orderings here, which is here, then you can use, for instance, the Spearman rank correlation or the Kendall-Tau distance to measure this distance. So the loss is defined. I cannot compute it, but it is defined. So what I want is to find a condition that is going to guarantee that if I fix some, if I set some epsilon and some delta here, then with a very high probability, which is close to 1, the loss will be very small, less than epsilon. Okay, so this is what I want to try to guarantee. without being able to compute this distance here. So I'm going to try to explain that on an example. So it is no, I work with a binary classifier. So we have some target classifier, say, which associates a value -1 or +1. The set of instances is pairs in R. And say, so this is something I take, for instance, if I have got, I've generated 10 random examples from the targets that you don't know yet. You will discover what it is soon. But if I generate these 10 random examples, I have got that. So the idea is of classification is what can I do to, what can I induce, what classifier can I learn from that? Of course, if you want to learn a linear classifier, well, in this case, there is not much choice. There is, you can see that the set of linear classifiers is pretty well defined. I'm not going to try to learn that. I could try to learn a square. This one is okay. This one is a rectangle. It is okay as well. Or an oval, anything. Okay, so at the moment, I don't know exactly what C is actually. So if I, the intuition still is that if you have more examples, of course, you know that you're going to learn in general better. It's not, maybe not always. So here with 30 random examples, not the same as before. It's another generation, but I've got this one. So well, here we can see it's still the same target classifier. So I can see that here, for instance, if I wanted to learn a linear model, it's not possible anymore. This shows that the other sample that I had before was wrong for that. So it could be that is another generation of random examples. Here I've got even more examples, so it starts to be a bit clear what the model could be. At least so we've got some idea. Okay, here we've got 100 of them. So still, it's I don't know what the target is. So now I make in order to learn, you've got to restrict the hypothesis space, and so here I make a big step. I say, well, I'm going to try to learn a circle which is centered at the origin. And so here there is not much choice. So it is another generation of random examples. I've got these examples here. Okay, I've got about 30 of them. You can see that I could make it a bit larger, but I cannot make it smaller. Okay. Well, here it becomes pretty clear what the circle is with 100 examples, that there's not much mistake anymore. The good thing is that if I know if I have a fairly restricted set of hypotheses, I don't need actually that many examples. That is important because it is going to have a big influence on what on the results that I will give later. The idea is that if you have a very constrained set of possible classifiers, then you don't need that many examples to learn them, to learn the right one, because fewer examples are going to be enough. So now suppose I have got this data here. So it's there are only 10 examples. And I decide to learn a circle that is centered at the origin. And I can learn the smallest circle. Let's say I've got an algorithm, okay, which is going to output. So the algorithm is just here. It just make the radius of the circle big enough to contain all the plus signs. Okay, so this is the smallest one. The smallest one, it contains all the plus signs. This is a possible algorithm. It is going to output a circle centered at the origin that correctly classifies the examples. Of course, I make the hypothesis here that the target classifier is itself a circle centered at the origin. Otherwise, I could not be sure that I could find one circle like that. Okay. This is just a choice. I could actually output the largest one, so the largest circle that does not contain any negatively labeled instance, or I could take the middle or anything. So there are a lot of possibilities. Anyway, I've got this this algorithm. I still have this unknown target, which has a certain radius that I don't know. This is the only thing I don't know with the target. I don't know its radius. I've got my set of examples. So here you can see, now you can see the target here. It is the same target that I was used for all the slides before. So now you can see it. And the question is, I have my learning algorithm. I have these examples. My learning algorithm returns the smallest circle that contains all the plus the positively labeled instances, examples. And so what I want is somehow to measure the distance, to guarantee that I'm not going to make such a big mistake. Here, the mistake is not big. Okay, I have a fairly small mistake. What is the loss here? So in binary classification, the loss is just the surface of the here of it's just the surface of this set R square, where I have a difference between the two, the target, which is the dashed line here, and the one that I have learned. Okay, so the one that I have learned, I write it H of A, this is the algorithm, and S, which is the sample. Okay, so this is my loss. My loss is actually the probability of making a wrong decision. Okay, if a new instance, suppose I have learned something here, which is this one. Now I've got a new instance coming. I want to classify it. If it falls here, it will be okay. The classification will be correct. If it falls here, the classification will be correct. But if it falls in the yellow area here, the classification will be wrong. Okay. So the loss is the probability that I am between the two circles, that a new instance that comes falls between the two circles. Okay. It is the probability according to some distribution, because when you've got a machine learning setting, you've got your examples. You don't know the probability distribution often. Sometimes you know, so you have some information about it, but often you don't know about it. And here we don't suppose anything about the probability distribution. There is a very slight hypothesis on the property of the distribution, but which is very general, which is not restrictive. So we don't know this probability distribution, but we know that the loss is the probability of having something that falls here, whatever the distribution is. Okay. So what is important here is that this loss, of course, depends on the sample. Okay. Here I have on the previous slide, I had a good sample with just 2 positive examples, but one which was close enough to the target so that I didn't make a big mistake. On this one, I still have only 2 positive examples, but of course, they are close to the center. They are far from the target. So if I have this sample, I will make a big mistake. Okay. So I am in a passive learning setting, so I have no control over the examples. I'm not. So now the question is, as I said, what is the probability of having a small error? Okay, you remember in my formula at the beginning, I wanted to find some guarantee on the probability of making a mistake. So can I say something? Can I somehow make some guarantee that I will have a small loss, a small mistake? And in fact, this question is, what is the probability of having a good sample? If I have a good sample, this one is not a good one. If I have a good sample, then I will be able to give a guarantee. And so what is the probability that the sample that I have no control over the sample, but if I have a good one, then the mistake will be small. Okay. So I'm not going to go in too much detail in this here, but the idea is that if I want my loss is bigger than epsilon, so suppose this is the area. So now I set some epsilon here, and I want to check when the loss is going to be bigger than epsilon. Okay, and the loss is bigger than epsilon if no positive example falls into this area. Okay, and what is the probability that an example falls in this area? If I've got one example, I draw one instance. What is the probability that it falls in this area? Well, it is epsilon, because this area has probability epsilon. I've defined it in this way. Okay, so just by considering that, I don't know the distribution, but I know that I can imagine this area with a probability epsilon near the border. And so I can finish the reasoning, and I can, at the end, finish my reasoning and say that the probability that the loss is actually less than epsilon, and I find a bound just by reasoning about the probability that an example, or one example first falls in this area, and then one example does not fall in this area, and then the fact that no example falls in this area. Okay, so this result in itself is not what I am interested in here. The only point here is that what I want to show is that you can just reason without being able to compute the loss here. You can reason, and there are statistical tools actually to bound this loss here, and to give some guarantee on the fact that you are not going to make a big loss. Okay, so this is just the final result. When we have a binary classifier, we can guarantee that there is a very high probability. And what you can see is that if m, when m increases, the number of m is the number of examples. So when this increases, of course, the probability of making a mistake tends to 0. Because the more examples I will have, the less mistakes I will make. Okay. Okay. So now, what is the sample complexity? Oh, plenty of time. So the sample complexity, I want to find a number of examples. We've just shown here that when m grows, then the mistake will be less and less. Well, the probability of making a mistake, the probability of making a small mistake will tend to 1. So the question is, can I, if I've got a set of an instance space, a hypothesis space, an algorithm that learns, can I find a function, a number of examples here? This is going to be the number of examples that I need, so that the mistake that I will make will be less than epsilon with a high probability. So this number of examples depends on the approximation that I allow, epsilon, and it depends on the probability, on the threshold of probability that I want to have. So this is the sample complexity of my, this is the way to define the sample complexity. I just want to find how many examples I need to probably learning a good approximation of my target, of my unknown target. Okay. Okay, so now for learning generalized additive utilities, you've got this sample complexity here. So this is let me. This comes from. I will show a bit later where it comes from. So what is interesting here? Recall, you want to make a small mistake, less than epsilon, with a high probability greater than I minus delta. So what does this formula says? This formula say that, for instance, if I want to divide the precision by 2, if I want to do something which is twice as precise, then the number of examples needed is going to be multiplied by 2. Okay, so this means that this formula is polynomial in 1 over epsilon, which is a good thing, and it is a polynomial. It's a polynomial with a small degree. Here we've got 1 of epsilon, so it's a maximum of these 2 terms. So here the term is linear in 1 over epsilon, so it is a fairly good thing. And here it is. You've got this term 1 over epsilon multiplied by a logarithm, which is fairly low as well. The best thing is when you have everything in logarithms, of course, but here it is not the case. It is not that good because if I want to divide my approximation ratio by 10, then I need 10 times more examples. Okay. The probability threshold. And it is often the case, it appears in the logarithm here. So it's the same. If I want to divide the probability of mistake by 10, then I need a logarithm of 10 examples. So it's this is a very low complexity as far as this delta is concerned. But the bad thing, of course, is it is these 2 terms here that you can see here. It means that the number of examples grows exponentially with the size of the clicks that I allow. So of course, we have seen that the size of the clicks, it was already important for the number of equations that for the number of variables that are generated when we try to solve the linear program. And so if you want to learn something with a big K, you will have big equations, so a system which is hard to solve. And if you want to learn something which is precise enough with a big probability, the number of samples, the number of examples that you need grows exponentially fast with K. So in practice, it means that you can only consider small Ks. K equals 1, of course, is the bottom line you can do, but you're not going to grow very fast to take big K. So there is this term, and of course there is this one, which is not beta. So n is the number of variables, and it is n to the k plus 1. So here you can see that this sample complexity depends in a fairly bad way in the number of variables. So that's well, one way of saying things is that, of course, if I fix a small k, then n is going to be a low polynomial of n, but still I think so. I'm not good. I don't know much about classifiers in general, but I think there are lots of domains where you do much better than n to the 3 or n to the 4 as a sample complexity. So this one it's not. But well, we are comparing. Well, we are trying to learn something which is difficult. We are trying to learn an ordering of things. So it's not, in a sense, it's not a surprise that you need a lot of examples to do that. It's a difficult thing. Okay. Okay. So this result just give you a brief idea of how it works. It is it is proved using a concept that is used in binary classification. Maybe I'll briefly describe it shortly, where you can see your preference model. You can see it as a binary classifier, because if I have my preference model, it can be an additive utility or anything else, and if I get and if I've got a pair outcomes alternatives O and O prime, my binary classifier says that this has label 1 if the left alternative is better than the right one, and it has a value of 0 otherwise. So this is just a simple classifier, and I can apply that. So I can try to learn, I can use the concepts that I use for binary classification to try to bound the sample that is needed, the size of the sample that is needed to learn. So this is how it works. And in fact, this parameter, the VC dimension, the dimension of Vapnik-Chernovenkis, I can't remember, can never say it, has this complexity. So this term here comes from the VC dimension. So the VC dimension, what is it? It is a measure of how complex your model, model is, your model space is. So with a big complexity, with a big term like that, it means that with generalized additive utilities, even with degree less than k, you have a high dimension here, which just reflects the fact that it is a very expressive model. If k equals 1, then of course it is going to be very low. I will have 2 n squared, so it means that it will not be very expressive. But if I have a big k, it is going to be very expressive, and not surprisingly, it is difficult to learn. Okay, so just a few things just to illustrate what it is, the dimension. The VC dimension, maybe I should, I don't have. Okay, I'll just do it here. The idea of this dimension here, it is a fairly simple concept, so it is a nice one, is how many, well, I do it on maybe on the board here. The question is, here I consider, I am in the plane here, and I consider how many examples, how many instances can I separate with a line, whatever the label that they've got. So I take 3 points here. And the question is, whatever the value that the label that I give to them, can I separate them with a line? So for instance, if they've got this, and this, plus, plus, minus, I can separate them with a line, obviously. Okay, this one works. If I give them the labels plus, 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 can I separate them with a line? Yes, of course. I take, for instance, this one. Okay, so it works. Okay, so this is easy to see that whatever the labels that you give, you will be able to separate them with a line. Okay. So now suppose, so this gives the result that the VC dimension is at least 3, because I was able to separate. I have found 3 points that I can separate whatever the labels. Okay, now, can you do that with 4? If I take 4 points here, so I have the choice. I can choose whatever points I want. Of course, I'm not going to take that. It is fairly clear that if I take that, I'm not going to be able to separate all of them. Clearly, if I take this, I cannot separate them. Okay, so I don't want to take them aligned. It was the same for 3 points. So the question is, can I find 4 points? So the idea, of course, is that you are going to do something probably as you want to put them somehow in a very separable way. But here you can see that you cannot. You will never. Well, I'm not going to demonstrate that. The demonstration is not trivial. But I think it is clear that if I take 4 points, there will always be one labeling that I cannot separate. Okay. If I get here, I take plus, plus, minus, minus. It doesn't work. With one line, I cannot separate them. Okay. And so you can try if you've got some time. But I do not recommend trying because actually it's proved that it's not possible. So don't do that. But anyway, and of course, if you can't do that with 4, you will not be able to do that with 5. Okay. So the result, which is a very well-known result, is that the VC dimension of linear separators in R square is 3. You can separate 3, but you cannot separate 4. Okay. So if I take the circle centered at the origin, well, this one is not so interesting anyway. It is 2. The VC dimension is 2. With circles, you cannot do that. With a line, you can see that you have 2 degrees of comment on dit? I can't say. Does anybody know how you say in English degré of liberté? Freedom degree? Yeah. Okay. But anyway, with lines, you have more freedom. That if you want here, this is very restrictive. I take the circle center at the origin, and I have only one parameter, which is the radius of the circle. So obviously, it is not very expressive, and it is not a surprise that the VC dimension is less than with the lines. In general, with linear classifiers, the VC dimension is n plus 1. Okay, and so this is interesting. No, that is not interesting. Well, so this is there is a result for the VC dimension of neural nets, but we're not talking about. I'm not talking about deep learning, so I'm not interested in that. So now there is a very general result here that says that if you've got if you know the VC dimension of your hypothesis space, so here my preference model considered as binary classifiers, then this very general result gives me a bound on the sample size that I need to get this small loss with a big probability. And the formula here, it is well known. There are a couple of, well, it is not always expressed in the same way, but you've got a few formulas that you can easily find in the literature on complexity, on pack learning. And it says that if the number of examples that you've got is greater than that, then you've got this which is true. So interestingly, so the VC dimension of the model is here. This is where we had this 2 to decay n to decay plus 1 in the formula for the general additive utilities. We have so this 1 over epsilon, this 2 over delta, and this 1 over epsilon here. Okay, so this is a well-known formula. Which the important thing is that the sample size, the sample complexity is linear in the VC dimension. So it gives if you've got the VC dimension, you somehow have a good idea of how difficult something is going to be to learn. So for learning an LP tree, what do we have? So I want to learn a K LP tree. So K is the number of nodes that I allow at each node. Sorry, the number of variables that I allow at each node. I will put a bound on the number of leaves. You remember with my LP tree, sometimes I have nodes where I will have a lot of children and sometimes just one. So I just want to, my LP tree, they always have the same height. All the variables appear in every branch, so they always have the same height. But I put a bound on the number of leaves. In order to be able to express something, I suppose that the domains of the variables all have size less than some maximum d. And I want to, so I am in the setting that I described yesterday, where I have this sales history, this list of cars or computers that have been sold. So I have this, I want from this multi-set of alternatives, I want to learn something. And so the sample complexity of this is, so you've got the formula here. So is it bad or good? One thing, yeah, there are good things and there are bad things. What are the good things? If you look at the logarithms, it gives you the good things. Everything that is inside the logarithm, it's, in general, it's good. So the good thing is that it is logarithmic in n. So that's a good thing. In fact, somehow it shows that LP3s have a good property. The fact that it is logarithmic in n is nice. It is, so the delta appears here, and it is in 1 over delta. So it is okay as well. For epsilon, it is not as good as for additive utilities, because instead of 1 over epsilon, we now have 1 over epsilon square. So it is not as good. It is well, it's not good. And the bad thing is here. That is not good, actually. This means that if you augment, well, it's not too bad. With this term here, if so this term is very pessimistic. If you have one variable which has 50 values, for instance, and all the other ones which are binary, this result gives a bound with 100 here, 100 to the power or something. So, but actually this so this is a big overestimate, because when we look at the derivation of this formula, we can see that, of course, if we knew that there is only one variable that has a domain of size 100 and all the other one are binaries, we could put a much better bound here. So this D here is not too frightening if you have only binary variables. So it's 2 to decay, and you're going to bind to keep small values of k, so it's not too bad. And this here is not too bad either. It is the width of your LP3, and it means that if you stick to, so in a simple model where you have a linear tree, which is the one for which we can compute, we can learn the optimal LP3. For a linear tree, this is of course this becomes 1, so it is not bad. If we try to learn something which is a bit more complicated, then this is going to grow. So we must take care to leave a bind on this. Well, we must keep the width of the LP3 rather low. Okay. Okay, I think this is it. Maybe I've been a bit too fast today. I've finished. I don't know if you have questions. There are many co-authors that wrote. There are some results, not all of them are, but papers that where I was a co-author, and of course, many thanks to the co-authors of these papers.